Okay, 5-4. We're only going to look at the intro first. So, translate the following into calculus notation. The volume of a cylinder is increasing at a rate of 6 cubic feet per second. So if it's increasing, we're talking about a rate, correct?
Yes.
So if it's increasing or decreasing, if we're talking about a rate, we're talking about the derivative. So the derivative of the volume, and specifically with respect to what? Time, because it was talking about seconds, right? Is 6 cubic feet per second. Yeah? So here, the depth of the water in a rectangular pool is decreasing at a rate of 2 inches per hour. So again, we're talking about a rate. So when we're talking about a rate, we're talking about the derivative. So the derivative of the, I'm going to say the height because I don't want to do d of d, with respect to time is equal to 2 inches per hour, but it's decreasing, so it should be negative. At rush hour, the number of vehicles going through the SunPass toll booth is increasing at a rate of 85 vehicles per hour. So the derivative of the number of vehicles with respect to time is 85 vehicles per hour, correct? Air is escaping a spherical balloon at a rate of 15 cubic centimeters per second. So if we're talking about inside of a balloon, you're talking about the volume of it, aren't you? So the derivative of the volume with respect to time, and if it's escaping, it's going to be negative 15 cubic centimeters per second. Make
So that
sense?
one didn't say increasing or decreasing, but it's still is at a
It's
rate.
escaping. Escaping.
Oh, so it's decreasing.
Yeah, at a rate. Yeah, if it's escaping, your volume's going to be decreasing, right? Just thinking of a balloon. All right. In the formulas below, take the derivative with respect to time. Remember to consider which variable changes with respect to time before you take the derivative. So looking at the area of the rectangle. So we're going to take the derivative of the area with respect to time, yes? And if you're talking about area of a rectangle is length times width, here we have to do the product rule. Do you agree when we take the derivative of this? Yeah? So I'm going to say length times the derivative of W with respect to time plus the width times the derivative of the length with respect to time. Make sense? Circumference. So the derivative of the circumference with respect to time. Now 2 pi is a constant, isn't it? So 2 pi, and we'd have the derivative of the rate, or the derivative of the radius with respect to time. Do you agree? Looking at 7. The volume of a cube, so the derivative of the volume with respect to time. Here, when we take the derivative of the right-hand side, we'd have 3s squared ds dt, right?
Why would we have DSDT?
Because it's with respect to time.
Okay.
So remember your implicit differentiation? When we did the derivative of y, we had to have dy dt.
Oh, yeah.
So if this
Same
were
thing
in-
here because it's got to be with respect to the same variable.
If this were in respect to s, then we would just do 3s squared.
Correct.
And if one
But-
of these is in respect of time.
Right.
Okay.
I get it.
Yep.
You just have to have the same variable. Okay.
Yep. So here we have the derivative of the surface area with respect to time equals 2 pi is your constant, so we can leave that out in front. But we're going to have to do the product rule there, right? So I could have the rate times the derivative of h with respect to time plus the height times the derivative of, not rate, but radius with respect to time, yes? So we have to have the dt there because the variables don't match. All right, so here, area, so the derivative of the area with respect to time is going to be what? 2 pi r, but we have to have the derivative of the radius with respect to time because our variables didn't match. Make sense? All right, perimeter. The derivative of the perimeter with respect to time would be 4, but we have to have the derivative of s with respect to time, yes? All right, volume of a cylinder. Derivative of the volume with respect to time would equal, we can have our pi out in front, or what, we're going to have, we could just do the derivative, we're still going to have the product rule, right? So I'm going to say that's 2 pi r times h, and I have to have dr dt. Is that fair? Plus, what, pi r squared, and then the derivative of h is dh dt. Is that fair? Yeah? All right, here I'd have dv over dt. I think it's easier to bring the constant out in front. So I'm just going to do 1/3 pi out in front. And then I'm just going to take the derivative of r squared h, right?
Yeah.
So I'm going to leave r squared, and I take the derivative of h is dh dt plus h, that'd be what, 2rh? Because I'm taking the derivative of r squared this time, so 2rh, and I'd have to have dr dt. Good? All right, the volume of a sphere. So dv over dt equals, that's all, you don't have to do the product rule, so I'm just going to go ahead and bring that down. You'd have what, 4/3 times 3, which would just be 4. Do we agree with that? 4 pi r squared, and we have to have dr dt, derivative of the radius with respect to time. Okay, side lengths of a triangle. So implicit differentiation here, yes? For x squared, we'd have 2x dx dt, fair? Plus 2y dy dt equals 0. Make sense? So that's just an intro. Now, what we're going to end up with is we're going to end up being given maybe dp over dt and solving for ds dt, or we're going to be given dr dt, or have to find it, and be solving for this. Okay?